Three different refrigerants, pretty much. So let me just get the slide sharing going, and then we'll take it from there. Share screen. So if I've pressed the right button, then you should all be seeing the first slide of the presentation.
Yes.
Yes, good. Okay, so I've credited my colleagues Chris Seaton and Sarah Kim for parts of this presentation, but also Ira Saxena, who's on the call today, is also a key member of our refrigerant development team, and in fact she features a little bit later on in the presentation. So I'm going to cover three different new refrigerants, or newish refrigerants today, and the background to this is these are all refrigerants where their application can be not just refrigeration or air conditioning or heat pumping, but in fact they can be applicable to all three of the main applications of the vapor compression cycle. The two newest refrigerants, if you like, are R-485A and R-492A, and most of the presentation will be talking about them, but I also wanted to highlight a refrigerant which we developed and launched actually in 2014, R-444A. Which is a medium pressure refrigerant. So I'm going to be covering the use of R-485A in transcritical technology and CO2 technology, really. And the reason we're covering it in that technology is the blend is 69% CO2. So it's CO2 with some fluorocarbon added to it to alter the performance parameters. And we're testing that actually in electric vehicle thermal management systems, residential heat pump water systems, unitary AC systems, and also commercial refrigeration systems. And I'll come on to that in the presentation. The other two refrigerants, I'm focusing on their use in Lorentz cycles. So this is where the source and sink fluids have temperature changes which are non-negligible. And this allows exploitation of the extra degree of freedom that a blend gives you in terms of the variation of temperature through the condensation or evaporation processes. But just before we dive into the numbers and the graphs, why develop refrigerants? Well, the decarbonisation strategies of companies and of governments are driving continual change in automotive engineering and also in residential and commercial sectors. You know, the F-gas caps in the main economies of the world are forcing people to make better use of greenhouse warming potential by restricting the total available supply. The other driver is that as we move towards more electric vehicles need thermal management systems. They don't just need air conditioning. What's thermal management? It's the art of making the best use of the heat, of the energy you've got, and moving it around the vehicle. So taking heat from where it's not needed and putting it in where it is needed. And why is heat needed in the vehicle? Well, it's needed for keeping the passengers happy in the winter, but it's also needed for keeping the battery happy. Lithium-ion batteries require, for best life and charge performance and so on, they require to be kept at around about our normal comfortable room temperature of about 20-21 Celsius. And they have to be kept at that temperature even when the car is switched off and not running. So fine, if it's a UK summer evening, the car will be pretty happy sitting close to 20 degrees most of the time, but the battery has to be kept at 20 degrees even in the winter. And so you need to move heat around the vehicle all the time. The single biggest impact on the range of an electric car is actually keeping the passenger comfortable. And in winter, the hit on the battery range can be as much as 40 to 50% of the total theoretical range of the vehicle for a smaller car. Even in summer, as that ambient temperature moves away from the comfortable temperatures that we like of 18 to 22 Celsius, then the hit on range also comes in. So evolution of thermal management means that, in fact, car systems are evolving to move heat not just from air to air, as in a classic air conditioning look, but also air to water and water to water. I'm using water loosely here. In fact, they're using glycol and even some more exotic fluids in some of the chillers. But it means that changing the refrigerant properties by designing a blend refrigerant can actually give a real positive gain to the performance of the system. Similarly, as we move from fuel combustion to electric heat pumps, we need to look at possible efficiency gains where we have sensible changes of temperature on the source side or on the sink side. So source side, canal water, river water, even groundwater type heat pumps. On sink side, any hot water heat pump has got a sensible temperature change of 5 to 10 degrees or maybe even more on the hot side. And as we look at the total environmental impact of heat pumping, once you drop the GWP of the refrigerant below 300, in fact, the environmental impact is dominated by energy efficiency, completely dominated. There's a rather good analysis of this in the International Journal of Refrigeration from a few years ago, which shows that how you'd arrive at that conclusion quite nicely. So if you have a lot of heat pumps, even a 5% gain over the fleet is a significant gain in environmental impact. So our refrigerant design goals then are really to design highly efficient refrigerants, where we're looking at GWP lower than 150. Flammability, we're focusing on non-flammable fluids. This is particularly appropriate for larger scale applications, such as some of the refrigeration type applications or building scale heat pump systems, where the constraints on using flammable refrigerants are challenging in terms of bringing refrigerant into the building, or weakly flammable refrigerants, the so-called 2L flammability, where the flammability can be managed quite easily by charge control and relatively inexpensive flammability mitigation around the equipment. Another design principle is we don't want anything to last a long time in the environment if the refrigerant gets out, so we want the breakdown products to be benign. And last but very much not least, better efficiency, because we're really focusing on environmental impact here. So I'm not going to go through every line in this table, but I put it in the slides on the assumption that afterwards, people that want to kind of get a copy of the slides and the numbers are in there for reference. Really, we're talking 3 pressure levels. We're talking about 485A being the similar pressure level to CO2. And we've been testing it and basically dropped into CO2 technology. Unlike CO2, that's got a critical temperature over 40 Celsius, which means it can basically run more efficiently in a much broader ambient temperature range than CO2 can. 492A then is basically the same sort of vapor pressure as propane or the 407 or 454B, 444C type refrigerants. So the critical point is very close to that of propane, for example, it's about 90 C, and the pressure levels are similar to propane. But unlike propane, it's got a glide, and deliberately we designed this refrigerant to have a glide of about 8 degrees, so that it would work well in chiller applications where you're moving heat between fluids, where there's a temperature rise or temperature fall in the source of sink. And finally, 444A, which is really a medium pressure refrigerant. It's the same sort of pressure level as 134A or 1234YF. However, unlike those fluids, it's actually a higher efficiency than 1234YF. It's closer to R12, in fact, than to 134A in performance. Very few people will have seen an R12 system these days, but it was more efficient than 134A on its own right. It was just pretty bad for the ozone layer. So the reason for including 444A is that it also has temperature glide. It's smaller, it's about 5 to 7 degrees, depending on the cycle conditions. But it can be used also in a Lorentz current configuration to give itself another 5 or 6% COP over what would otherwise be achievable. I'm going backwards about that. So coming on first to 485A. So the point of this fluid is to exploit the developments of CO2 technology and to exploit the good features of a CO2 cycle, but to ameliorate the bad features of CO2. And what are the bad features? Extremely high operating pressure, extremely high compressor exit temperature, and rapid degradation of cycle efficiency as the ambient temperature goes much beyond the critical temperature of CO2 itself, which is 31 C, of course. So the blend is 69% CO2 and it's 21% R32 and 10% of R1132A. It's non-flammable. Its critical pressure is actually similar to that of CO2, but its critical temperature is 10 K higher. And that makes all the difference. The performance as a result is improved, and also with the lower operating pressure in practice, it can run to a much higher ambient temperature range than CO2 and still be acceptable in terms of the compressor performance. But we'll get into more of that as we go through the testing. So I have some numbers from different types of application here to share with you. The first is, again, one of these electric vehicle thermal management systems. This is a combination of air conditioning and heat pumping, and although it's maybe a little bit outside the normal remit of ASHRAE, which tends to be building focused, I'm including the data because it gives a good insight into the effect of ambient temperature and performance. And I've got some data on a residential heat pump water heater. We've done some work on an air conditioner heat pump as well, and I'm going to talk mostly then about commercial refrigeration, which is a live test project that we're running right now. So electric vehicle thermal management system, this is actually a system from a Volkswagen car, the ID.3. Very similar technology actually across the Volkswagen range. So if you have another ID model, it's an ID.4 or ID.5, and you ticked the CO2 refrigerant option when you bought the car, then you'd actually have the same underlying air conditioner heat pump cycle. So it's actually quite complicated. It's got a liquid chiller, and the liquid chiller is to keep the battery happy. So it provides cold liquid to maintain battery temperature during exothermic behavior, charging or rapid discharge. It's got an HVAC evaporator for air conditioning. It's got an HVAC gas cooler for heat pump mode, and it's got an outside heat exchanger which works as either a gas cooler or an evaporator, depending whether it's running as a heat pump or an air conditioner. It uses a hermetic scroll, so it's the sort of technology you might expect to see in supermarket refrigeration, but it's bolted into a car. And it can run from -20 C ambient air temperature in heat pump mode, all the way up to +60 C ambient temperature onto the gas cooler. So really quite a broad range of application and considerable requirement for flexibility in operation, compared to, say, a simple condensing unit designed for keeping a cold room at a constant temperature. So we tested this unit in a German specialist laboratory that works a lot in the automotive systems, called Epitronic, and we did air conditioning mode testing, heat pump mode testing, and we did optimization strategy testing. So we didn't change any of the hardware, but we did change the control strategy for the blend, both in aircon mode and in heat pump mode. So in air conditioning mode, what we found was actually better than we'd first expected from thermodynamic modeling, but we're comfortable with the results, having gone through the analysis in detail. And what we found was that across the board in air conditioning mode, we had a COP gain that ranged between 15% compared to CO2 up to 25%. The bar chart shows the performance points in terms of capacity or COP in relation to the measured CO2 values. There's a whole load of points there, but basically, if you want to get a shorthand feel for it, the highest air temperatures are on the left and the lowest air temperatures on the right. And the numbers along the bottom denote the air temperature onto the gas cooler, or the outside air temperature, if you like, going into the system. So 60 C is the hottest temperature, that's on the left. And then on the right, we have 15 C. So 60 C is a hot summer's day and you're stuck in a traffic jam. And 15 C is a more typical spring to autumn type temperature in most of Europe, where the cycle's running a lot more gently in terms of pressure. But you can see the orange bars here are the COP, and they're always better than 100%, and they go as much as 125%. The green bars are the actual cooling capacity of the evaporator, and that's the combination of the chiller load and the aircon load. And you can see the green is generally the lowest it gets is 95% of CO2, but most of the time it's at 100% CO2. Once the ambient drops below 25C, actually the compressor isn't running all the time, and so the capacity would be exactly the same as CO2 because it'd just be cycling to match the load requirements. But at the left-hand end, the extreme temperature end, you can see, for example, at 60C point, it has a much higher capacity than CO2. That is actually because the protective systems in the compressor wouldn't let it run at full speed with CO2 for 60C. The discharge pressure was over 125 bars and the discharge temperature was over 170C, and the system's inbuilt cutouts wouldn't let it run at full speed. Whereas the blend running much lower pressure was able to maintain full capacity, and hence the large disparity in apparent capacity. And what we found was we'd basically used a heuristic to use 85% of the optimal CO2 pressure at each state point, and that gave those results. We found if we then did a more detailed COP optimization study at 35C, we could squeeze another 4% out of the performance. So we could lift that point up from 19% COP gain to 23% COP gain, just by moving a couple of bar on the exit temperature. And in terms of evaporator temperature distribution, we saw no issue, no issue with air temperature quality, and no issue with frost formation. So very encouraging results, and it would be directly transferable to, for example, to a stationary cycle running in sort of 0C evaporator with ambient air as the heat sink onto the gas cooler. When we went into heat pump mode, we tested the blend twice, first with the same control strategy as CO2, where we got comparable performance, but not much different performance. And then we changed how we used the gas expansion valves for the blend. And that was to move the load around between the two internal heat exchangers. So we had a different distribution of heat transfer across the heat exchange surface. When we did that, we found that we could get 20% COP gain compared to CO2. And the 3 points here are 0C, -10C, and -20C. And at the first two temperatures, 0C and -10C, we had 20% COP gain. And at the lower temperature, we had 10% COP gain. And we expected the COP gain. We were pleasantly surprised that the COP gain maintained even down to -20C. And in these points, with the same delivered heating capacity. Quite an arduous heat pump cycle, air delivery at 50C with a cross-flow heat exchanger, and external air at -20C. That makes a really quite a large pressure ratio even for CO2. And so we're pleased with the performance. This is certainly better than you get with fluorocarbon refrigerant over the same sort of temperature lift. This COP of 3.3 or something like that at -10C ambient is really very good. And to make sure it wasn't a fluke, we tested the system again with a new control strategy with CO2, and it basically made almost no change to the performance of CO2. I think it gave it 0.5% gain in capacity in COP. So it was a good illustration that although the blend can work in a CO2 system, soft optimization is useful to get the full benefit of the different thermophysical properties. We also tested it in a residential monoblock heat pump water heater. This is one you can buy today off the shelf, and indeed that's what we did. We tested it on a drop-in basis. I've not included those numbers per se because we actually published them in a prior conference. The numbers were good. We saw up to 30% COP gain, but it was very difficult running on a drop-in to ensure we had comparable conditions. And also with the size of the system only being 4 kilowatts, the errors of measurement we felt were probably quite significant, and so they were a guide that the COP would be significantly better, but they weren't necessarily as accurate as a calorimeter. We actually took the equipment apart, and we did this in collaboration with Cambridge Refrigeration, and we rebuilt it so that we could get direct control of all of the main variables inside the unit. Very simple cycle, very crude internal heat exchanger, single stage compressor, and basic cross-flow gas cooler. So it's not the most sophisticated CO2 system, but it works pretty well. So the following graphs are just a couple of points we did to match the standard for heat pump water heater performance testing. I think this point is A7W35, so that's air at 7 Celsius, water return from the house heat system at 35C and going back out again at 43C. And what we saw here is in the two graphs are peak capacity as a function of gas cooler pressure, and then heating COP is a function of gas cooler pressure, the blend being in blue and CO2 being in orange here. And you can see here that we achieved about 4.8 kilowatts with the blend and just over 5 kilowatts with CO2. The rated capacity is 4.4 kilowatts for the unit, COP 4.6, and we matched that with both refrigerants pretty much. In this unit, we had a 10% COP gain at this point. And you can see from the gas cooler pressure, the peak COP for the blend was around about 65, 66 bars. In fact, it was not running in a transcritical cycle at peak COP, it was running in a subcritical condensing cycle at that pressure. Whereas for CO2, the peak performance was around about 80 bar, so transcritical cycle. Similar results, 85, 86% of the CO2 pressure in the gas cooler and about 80% of the CO2 pressure in the evaporator for this test point. Then moving on, we're running right now some more testing in our commercial refrigeration systems. This is a larger unit. This is a condensing unit. It's 16 kilowatts nominal capacity at minus 10 C. So it's a sort of large system with maybe 8 to 9 kilograms charge that you might use to keep a cold room cold or a walk-in freezer cold. And it rejects heat out through a gas cooler, but it's got a more sophisticated compressor. It's a two-stage rotary scroll compressor. The gas from the first stage of compression is cooled with ambient air before it's injected into the second stage. The cycle is also economized, so the hot, high-pressure gas is flashed down to an intermediate pressure to a flash tank, and then the flash vapor is taken into the second stage of compression along with the cooled gas from the first stage of compression. Then finally, the liquid from the flash tank is metered into the evaporator. So you get the benefits of the economized cycle effect here with better heat transfer in the evaporator with less flash gas going through the evaporator and reduced compression work overall. We finished a baseline on the unit with CO2 and we basically tested all of the medium temperature rating points from the European standard. And the measure performance, happy to say, is very close to the catalogue data. It's actually slightly better, but you'd expect it to be slightly better. We've got enough information to back out the compressor performance map, for example. And where we are now is we're doing charge determination for 485A. We had one run at it, but we got the charge determination wrong and flooded the economizer. So we're going again with less charge and hoping to have results in the next couple of weeks. But what we do know is similar to the heat pump water heater I talked about earlier, at 32C ambient, the blend sits as a condensing subcritical refrigerant, not as a transcritical refrigerant. So what do we expect to see? Well, we haven't got the measurement yet, but coming soon. We'll be to present them in Birmingham, in Manchester in August. If we take the data we do have and build a cycle model and take into account the heat exchange areas and so on, what we can predict is that we should be able to get an optimum COP for the blend that's 25% better than CO2. The top graph on this slide shows the effect of interstage pressure for the compression path on the COP of both refrigerants. So CO2 here is in blue, and the blend is the orange curve. And you can see the peak for the blend is about 2.9 COP with an interstage pressure of just over 40 bars. The peak for the CO2 is 2.3 an interstage pressure of about 55 bars. In fact, the unit control, when we let it run for the baseline, had the interstage pressure slightly lower than that at about 48 bars. And I think that's because the unit's designed to work over a range of conditions, and so the optimum strategy isn't necessarily to go for the absolute peak COP at this condition. But it's ever so slightly, it's only 2.2 versus 2.3, so it's basically almost identical COP at that rating point. And the purple square on that graph shows our measured data, and it sits exactly on where our model sits. So we're comfortable the model is realistic. So that says that we should be able to get 25% more capacity for this, more COP for this blend in this technology. How does that compare to a fluorocarbon condensing unit? Well, I deliberately haven't shared any specific details of manufacturers' condensing units here, but having gone over a range of condensing units from a couple of the leading suppliers of units and looked at the COPs you might get with 448, 455, 444C blends, typically for a fluorocarbon and a -10 plus 32 rating point, you might see a COP in a condensing unit between 1.9 and 2.1, so about 2. So the CO2 system on its own is already 10% better than a typical fluorocarbon system. The catch, of course, is it's considerably more expensive as a first cost. But with the blend, we can get another 25%. So that starts to make it interesting. The other points to note here, the bottom graph is just a readout of the points from several hours of steady operation. You can see the only takeaway from here is the unit controls itself very, very well and very stably. The rated capacity sits more or less at 16 kilowatts all the way through with very little variation. The power draw stays the same and the COP is almost constant. The points to note again, the evaporator pressures are lower with the blend, 19 bar compared to 27 bar, and the condenser pressure, 65 bar, again a true condensing pressure compared to 85 bar for CO2. So that gives one last clue as to what an attractive use of this fluid might be in the commercial refrigeration context. If you consider making sanitary hot water, domestic hot water is the other term often used, DHW, that needs to be 65 to 70 C, maybe even 75 C for bathing and washing, food preparation. If you're making up water, and the water typically would be between 8 and 14 C out of the tap, then a CO2 heat pump is more efficient than any fluorocarbon or even propane heat pump for that specific application if you get the technology design right, because you can glide match in the gas cooler. And that means you can get a much better overall COP than if you're condensing at a few degrees above the exit temperature of the water. When we ran the monoblock, we ran a domestic hot water point, and we found COP and capacity gains compared to CO2. So with the more sophisticated condensing unit, with its twin stage compression technology and potential for even higher COP gain, then that suggests that integration of a condensing unit for a cold room or a walk-in freezer to the hot water supply for supermarket food prep area could really be quite an attractive option that would let you do heat integration across the store more efficiently and would also give you nice hot water at a low COP and at the same time as cooling at a high COP. So that's enough about 485A. Quick check on time, we're doing fine. I'd like to talk about 492A next. 492A is a blend of 1132A vanadium fluoride with R32, R152A and 1234ZE. It's formulated quite deliberately to have temperature glide, and that is because we're looking at chiller applications. And I'm using the term chiller here to mean units that are designed to cool a liquid to produce heat as well as cool a liquid to produce cooling. The well-known Lorentz cycle here is the appropriate comparison, not the Carnot cycle. So the concept is that we match the temperature change of the fluid, the refrigerant, to the temperature change of the external fluid. If we do that, then the Lorentz theory tells us that the average temperature lift for the cycle is reduced and hence the COP is improved. In fact, in practice, if you do that, you get added benefits because you will help the compressor you'll typically reduce the pressure ratio in the compressor, and that means for a recip you'll get a better volumetric efficiency, and for a scroll type compressor, if you get the volume change right, then you'll get a better volumetric efficiency and a better isentropic efficiency. Best efficiency gain on Lorentz cycles, you match the temperature change of the fluids. So the worst case for a Lorentz cycle is a single fluid where you're a pinch at one end of the heat exchanger. So on the left I've shown air-to-water cycle for propane, and you can see for the conditions I picked, which is actually the fairly typical for a heat pump in winter, if you like, where you're trying to make domestic hot water for an old-fashioned radiator system. Then you might have the actual mean evaporator temperature being -3C and the condenser temperature being +74C to give you a hot water flow return 70C, 50C. Whereas you go to 492A on the right, exactly the same terminal conditions for the source and sink fluids, but now the cycle is running between -3C and +61C. So we've dropped the average condensing temperature by the difference between 74 and 61, 13K. That makes a big difference to the overall performance. And you can see here, if you do follow the numbers through, then you would get a 22% higher COP than with propane. Now, what's the catch? The catch is the area of the heat exchanger is basically proportional to the gap between the source temperature line and the cycle temperature line. And you can just glance at the graph and see the area in the blend must be much bigger than the area in the propane cycle, because the blend is a much smaller average temperature difference. So if you don't want to spend more money in the condenser, then you don't get quite as much gain, but even if you keep the same size of condenser, you will get a 10% gain in COP. So it's worth having. And if your technology is based around, say, plate heat exchangers for the condenser because it's hot water, actually adding 20-30% more area doesn't add 20 to 30% more cost, because the number of terminal points is the same, it's just some more plates in the stack. So the marginal cost is not so great. So if we then take that concept and apply it to some of the thermal management systems, the car guys need air at 50C for the cabin, which means the water temperature, the heat sink temperature has to be at least 55C. The two graphs here are the effect of ambient temperature on capacity or COP. And the graphs here are baseline relative to propane. So on the left we have heat pump mode, -20C. We're predicting capacity about 97% of propane, basically the same as propane. And then actually the capacity climbs above that of propane as the ambient temperature warms up towards zero. And the COP is pretty much consistently just above that of propane. So, well, what's the point? You might say, why not just use propane? Well, the answer is propane definitely has to stay in a secondary loop because you can't risk it leaking into a passenger cabin. But with this blend, you could actually have it doing direct air cooling. If you do direct air cooling or direct air heating, where it's directly on in heat exchange with cabin air, then you can add 10% to these COP values because you cut out one of the temperature differences in the cycle. And if you do that, then you actually have a beneficial effect on the range of the car as a whole. In AC mode, the differences are starker. If you look on the right-hand graph, that's AC mode where the evaporator is fixed at around about 2C, just above freezing point. Blue is capacity, so the blend here has got a higher capacity than propane, 15% higher in fact. And the COP is, again, about the same, to rising to slightly better. But with the thought that now with higher capacity, you can have your compressor running quieter. One of the quirks of the car AC world is that the engineers have to think as much about noise and vibration into the cabin as they have to do about performance, because people notice compressors rattling and whining away. And so being able to turn the compressor down is actually a big benefit. So that's where we are on that fluid. Testing is ongoing. There's a much more detailed study than this modelling study underway. and it's covering both air conditioning and heat pump performance. It's a big industry project. Many of the car makers involved, many of the technology companies involved, and refrigerant supply companies as well. We've just got the first results from 492A. I can't share them yet because the project's ongoing and it's a collaborative effort. So when the project concludes, then there will be presentations of all the results in public. But what I can say is the numbers we've generated show the potential of the Lorentz cycle to significantly alter the performance of a blend relative to a pure fluid. So watch this space, and we'll say more when we can. And coming on next to the lowest, so I've been cascading down in pressure. I started high, I've gone to the middle now, gone to propane, and now I'm coming down to 444A pressure level. So we developed this blend originally to drop into 134A technology for the car industry to consider as an alternative to 1234YF back in 2012, 2013. It still is being sold now as a drop-in for automotive AC, but it also has potential for application in other technologies such as heat pumping or refrigeration. We've done a lot of work on this. We did a multi-million-dollar project over several years with many of the car guys to prove all aspects of its performance and its implementation in cars. And what we can basically say is it's the same performance level as R134A, but its GWP is only 88. It's based in 1234ZE. We've got an ongoing employee long-term trial which ERA manages, and we've got something like 40 cars on the road with 444A, which have been running for 1 to 2 years without incident. My own car was converted 16 months ago, and we did a gas service on it last year. So we can say that even with it being a reasonable vintage of car and having lost 20% of its AC charge, the composition of the blend didn't shift at all in the year between services. The performance is excellent throughout. But we also have some test vehicles, and you can see in the photograph that's one of our test vehicles fitted with 444A refrigerant. And as ERA manages the program, you can see that she's there in the foreground. We are selling this into automotive aftermarket in Britain and North America as well. But we're also looking at it seriously for electric vehicle systems because of the ability to use the Lorentz cycle in chiller mode. It's proven to be both higher capacity and higher efficiency than 1234YF. You can see the pull-down graph here is done at a test facility in the Midlands, and this shows what happens to the cabin air inside a Ford, in fact, inside the very car you see in the photograph. It's the same car, where we pull it down from a hot soak, and it starts off at 60 Celsius inside the car. It's really very uncomfortable getting inside it. And then you put the AC on full and run it and see through a speed cycle and see what happens. And basically, in that drop-in pull-down test, the blend gets to the target temperature 4 minutes before it does with YF, and the system's designed for YF. The other point to note is that the steady state, when the control system lines out and it goes into steady operation, it's consistently delivering colder air than YF. So in terms of passenger experience, colder air faster. We're proposing it for automotive service as a sort of cost benefit primarily to the end user, but for original EV build, it's also got attractive features for heat pump mode. It's a higher pressure refrigerant, 1234YF, so it can actually go colder in heat pump mode than YF can. And as it doesn't contain 1234YF at all, it won't make trifluoroacetic acid in the environment. So just another note on how it could be used in a Lorentz cycle. Again, because of I can't share CRP data yet, but I can share model data. So this is a 444A compared to propane, and this is AC type point 45C inlet temperature to the condenser with an 8K glide, and 5C on the cold side as the evaporator heat source, and the baseline is propane in this instance. I wanted to give it more of a challenge. Putting a YF would be too easy. It would look so much better. So propane here is the base case, and you can see with the base case cycle, we get COP of about 1.8 for propane and 1.9 for the blend. Capacity is higher for propane by about 20%, but the operating pressures are lower for the blend, but still positive at these conditions, so that's fine in terms of keeping the compressor happy. And very similar exit temperature for the compressor. So that's base cycle is shown on the top right in the temperature entropy graph. Again, you can see with the glide matching, we're keeping a more or less constant temperature through the evaporation, or temperature difference, sorry, between the evaporation and condensation processes. Then the question is, can you gain more by adding more area to the heat exchangers? The answer is yes, of course you can. Eventually you get to the point where you've spent more on the heat exchangers than anything else, and it makes no sense. But if you start at 100% area and then add area, what happens? Well, with propane, if you add 20% more area, you get 6% more COP. If you add 20% more area to the blend, you end up with a 14% COP compared to base case propane. And it's actually, although it's maybe not too obvious from that 3-point graph, the gap between the two fluids opens up. So if you went to 30% area again, you would get more benefit for the blend than you would for propane. So again, this is something we're actively working on right now, but it shows how, with a bit of intelligent thought about the thermal properties of the fluid, you can take the same hardware and squeeze useful performance gain out of it. So last little point, I'm aware I've been talking at people for almost 3/4 of an hour, and you probably want to either ask questions or go and do something else. So just a word on materials. A lot of what ERA's team does in our lab is actually testing materials compatibility and lubricant properties and lubricant behavior. And what we can say is we've done a lot of work in the last few years in all of these fluids. And there's really no cause for concern that we can see. There are a number of acceptable commercially available lubricants out there to work with each of the fluids. We don't see any real issues with refrigerant breakdown. We don't see any real attack on metal, even the presence of air and water when we do stability testing. And if you want to know more about that, then get in touch with ERA and she will bombard you with facts and figures and photographs. Interestingly, we've found some other little side benefits. What we do know is 1234ZE is really difficult to polymerize. In fact, it's almost impossible to polymerize it. So there have been some instances in automotive aftermarket where poor system hygiene and maybe poor workshop practices has led to people polymerizing 1234YF in their service equipment. We don't see that as being possible with 1234ZE. And ERA's team have been doing a lot of work to demonstrate that. We can generate solubility data, Daniel plots, and so on. Interestingly, we found with 485A that we saw the blend is actually fully miscible with some oils, whereas the oils are not miscible with either CO2 or 32. And we think it's because actually the CO2 immiscibility with the lubricant and the 32 immiscibility with the lubricant are for different reasons. And the blend actually cancels out those reasons and brings the solubility back to the point where you get a fully miscible system across the range of compositions from 0 to 100%. It's one of these maybe not too important but quite interesting quirks of thermodynamics and solution chemistry. But the takeaway process is that this blend can be used with CO2 lubricants. In fact, the lower operating pressure means the lubricant will have less refrigerant dissolved in it. And so it might be possible as we really get into optimization for the blend to go down a viscosity grade and get a couple of % more COP out that way. But that's for future study. And we've also been generating data packages for compressor suppliers to evaluate and help them get their end users comfortable with using these refrigerants. But the big story for materials compatibility is these refrigerants have compatible solutions out there in terms of polymers and in terms of oils. So to wrap up then, really, I guess an underlying theme of this presentation is that these refrigerants don't just happen, they're designed. And we've designed these refrigerants to give high performance whilst keeping GWP as low as we feasibly can. And what we think we've shown is that you can have weak flammability or even no flammability in use. You can have the GWP below 150. You can design refrigerants without persistent environmental degradation products, and you can get better energy efficiency than alternatives. So the takeaway here is that these refrigerants have been designed to do as many good things as we can and minimize the bad side effects. And that we hope that the implementation of them will lead to an overall improvement in environmental impact of air conditioning and of heat pumping. Right, that's the end of my my talk. Thank you all for bearing with me. And I guess we've got a few minutes left for questions.
Cheers, thank you very much. Really appreciate it. Quite insightful. I'll open the floor to those who want to ask questions. If not, I've actually got a few questions that people have sent over, which I'll ask, but I'll give the floor a few minutes to ask if anyone has any.
Yeah, I'm just going to get into the chat and see if there are no questions appeared there yet.
I've got a hand up. Please put your mic on, ask your question. Thank you. Mr. Abdurrahman, yes.
You're on mute.
You're on mute, yeah.
Let me see if I could do it.
You might be able to do it.
No, I can't do it. Okay, I've allowed the mic, so you should be able to unplug your mic and ask your question. It's still on mute. Okay, what I'll do until we hear your voice, I'll ask a few questions in the meantime,
sure,
but keep trying to turn your mic on, Mr. Abdurrahman. So first question I got is, with the rate that you're having new refrigerants coming into the market, being developed and being designed, what is the impact on plants that are not really being as developed at the same rate? Is there much of an impact on systems or not really?
Do you mean the manufacturing units or the technology themselves?
I think they're referring to systems themselves, so the system itself. So whether it's a car system or
yes. Well, what we try to do is work around existing technology as a base. The car industry is a good example of this. Prior to the introduction of the F-gas directive, the MAC directive, every car's AC was basically the same. It was a very simple 4-box vapor compression cycle, evaporator, compressor, condenser, expansion, with a receiver built into the condenser. And the performance was kind of the same across, it wasn't basically built to a budget for mass market, as you'd expect, with something like 100 million new cars a year worldwide. And when the F-gas directive came in, because the regulators had underestimated the technology challenge of changing refrigerant, the timescales were actually very challenging. And so the absolute scope of refrigerant requirement was minimal change to the system, because we don't have the time to qualify radically different changes to components or even compressors. And in the end, that's why one of the reasons why 1235YF won out for that system was it was a basically no change drop in. They did actually have to introduce internal heat exchange to the cycle to get back to 134A performance levels. But that was a technology that was already developed. It just didn't normally use it because it cost more. But with that adoption, they could do it. Now, where we get to now is the car guys are moving away from that concept. They have to move away if they want to do thermal management. And so there's been quite an explosion in people trying out different designs of heat exchanger for chiller augmentation, different designs of evaporator. And I think we'll see the penny is starting to drop that by using the refrigerant properties as a variable in your design, you can actually get better overall performance, and so you will see some evolution. What is likely to happen then, the way the car industry works, is that the technology providers, of maybe half a dozen big tech companies, they will probably converge in parallel to similar looking cycles with similar features, whether it's economizers or it's reversing valves and so on to temper the glides, but it will be different to what's in there today. In the stationary sector, it's always a challenge. If you look at the evolution of the CO2 condensing units, and the two main ones you can buy today would be the Panasonic technology and the Danfoss technology, the Optima unit. They're quite radically better than the so-called not Nikodan, but the Japanese consortium CO2 hot water heat pump, which is again quite a simple cycle. To get acceptable commercial refrigeration performance, people have had to go to two-stage compressors and had to go to economized cycles. If you look at the technology used in large-scale CO2 supermarkets, we have these banks of ejectors to recover expansion work and claw another 10% COP back to get it back in the same ballpark as an HFC refrigerant. At which point alarm bells should be ringing about that maybe that's not the best energy efficient technology, but there we are. There are other drivers for the CO2. So I think one of the more resistant markets, again, because it's cost conscious, will be when you look at unitary air conditioning and small heat pumps, where again, the cycle design and the equipment haven't really evolved very much in decades. And budget constraints mean that these guys will really resist even something simple like putting a bigger suction line pipe on if it adds to the unit cost. Because as long as you meet your energy efficiency requirements, there's no benefit in going above them. So if, say in America, SEER 15 unit, you don't get any brownie points for SEER 15.1. You don't get any ticket price advantage in Walmart against your competitors at 15.0. And so the commercial drivers tend to damp down new technology adoption. But the GWP pressure combined with an ongoing realization, you do need to focus on efficiency. I think we'll see evolution in that sector as well. For a heat pump water heater, where you've already got counter-current flow and already got plate exchanger technology, it's a no-brainer in my view. Adopting to a blend with a glide should really be very straightforward.
Brilliant. Cheers. Thank you very much. Mr. Abdurrahman, I'll have another go. Let's see if your mic's on this time.
Now, okay.
Yes, we could hear you now. Yes.
Yeah. Thank you, Prof. Bob Law, for your very valuable presentation. And really got today from we got from you very valuable information concerning the new refrigerants and especially the refrigerant is R-444 and R-485A and R-492A. As understood from your valuable presentation, the R-485A, this for deep cooling, for the application of refrigeration, and the R-492A, this for chillers, and R-444, this for motor vehicle and electric vehicle application, air conditioning application.
Yes.
So yes, as we saw from your slides, the R-485 suitable best practice application for the freezing and refrigeration for -20. And this application suitable for the two-stage compression refrigeration cycles. Just in I'm asking about the cascade system. It's ultra low temperature refrigeration. This for the biomedical refrigerators and cryogenic refrigeration. This evaporating temperature for 86 centigrade, which the ideal refrigerant. This now undergoing in application of this equipment.
Well, that's a different fluid, and we've actually got a solution for that temperature range as well. We've got a blend which again is more than 50% CO2, R-473A, which is 473A with a little bit of R23, R-1132A again, and some R125. The total GWP of the blend's about 1800. So compared to R23 or R508, which are the two main refrigerants used for biomedical freezers, it's about 90% GWP reduction, but the performance is very close to 23. The high CO2 content means the operating temperature limit is about minus 70 C cold space temperature. So it won't go all the way to minus 86 because the CO2 starts to drop out and become dry ice. But for a lot of the ultra low temperature market, the fish freezing, for example, and fish transport, and for climate chambers, then minus 70 C is good enough. We do actually have a variant in that blend in development, but we're not taking it forward just yet because we're waiting to see if the potential is sufficiently large to justify the effort of commercializing it, if you like, and taking it on. But we know we can get down colder by altering the CO2 content in the blend. And then it's a trade-off of GWP and flammability and desirability. The 485A refrigerant has the same sort of lower operating temperature range, about minus 70 C, as 473A does. However, when you look at the compressor characteristics, it would run the compressor extremely hot. So it would require liquid injection cooling, which would actually take some COP and some capacity away. So although it's attractive, and we are working with one company that's looking at it for minus 70 C, we know quite a few system changes would be needed compared to the current ULT technology, which is basically just a cascade of minus 23 in the bottom or 508 in the bottom into something like 448 or 452A in the top stage. But there are technical solutions. We're working to see if it's a solution that actually that specialized market wants us to bring forward. But if they do, then we'll have one there. So again, if you want to know more, get in touch with ERA in the first instance.
And for cask system, also we use this type of refrigerant also.
Yeah, well, we're looking at we're working with one company, and we can't say too much more because of the confidentiality. But we are looking at basically GWP 150 on the top, and then what can we do in the bottom. So that's work in progress. But 473A has been really quite successfully adopted by people on land and at sea, I can say.
Is there any update for the F-gas regulation? The latest update in 2014. Is any update for concerning this new refrigerant?
That blend 473A's GWP is 1800, and the current threshold is about 2500, I think, for minus 50 C and colder. So it's comfortably under. And in fact, if you in America, there are some exemptions, but people, even where it isn't directly constrained, some system makers want to move away from 23 because of the extremely high GWP. So we're working with people in all three of the main continents right now on that.
Yes, but you know, for R32, facing many problems concerning the lubrication, solubility, and the ignition level, also for safety. Yeah. Because you cannot charge a big capacity unit by this type of refrigerant, only for a small unit.
Yeah. Yes. Yeah. The charge size limits in EN 378 I mean, a single split system, you're looking at about 4 to 5 kilos of 32. So that's, in American parlance, it's about a 3-ton unit, 9 kilowatts.
Have you any suggestion for technician that need to promote the certification for the certification among the technician?
There are some very good guidance notes through the British Refrigeration Association and also the Institute of Refrigeration. So their websites are good places to start for technical guidance and safe management of flammable refrigerants. I think we have a hand up there.
Yes, we've got two. So the one, you could ask your question first, then Ira could go after the one.
Yeah.
Thank you.
Yeah, sure. Thank you very much for the insights regarding the refrigerants. I just I got loads of questions, but I just briefly ask. First one, regarding the R-485. I'm curious about for R-485. So especially in winter conditions, so how much mileage you can increase after replacement? Do you have any kind of figure?
Well, we did try to do this, but we actually found it's very, very difficult to alter an electric vehicle control system. You can do it on the bench reasonably easily, but when it's integrated to the car, it becomes part of this big computer that is the car, and the trying to override the car control tends to make the car feel it's under attack, shut down and cry to the parent company for help. So we actually bricked the car a couple of times trying to program it to use the blend. And I had to get the Volkswagen technician to come from the nearest dealership and reset it, basically. So it's really, we had hoped to basically do drive cycles with it with optimum performance and then estimate it. But we did some modeling. We did some very well. When I say we, our partners Myra in Nuneaton, they built a so-called digital twin of a car, and we looked at simulating the journey from, I think it was our headquarters in Boston to Houston, and I think we concluded that even with the very poor data that we'd measured when we did try to test it in the car as compared to the bench data, then we would still save something like 5% of the battery life. And if you added, and the car results from the test track were basically the same almost the same COP as for CO2, because it was running it like it was still CO2. If we plugged in our thermal management bench testing, we probably expect to get another 10% range, something like that. But again, it's all you can really say is anything, because if you look at the passenger comfort being one of the biggest single drains on the car system, anything you can do to materially change that COP upwards by more than 5% in the 15 to 20% range has to be a good thing. But it requires literally like $1 million test program to prove it in a vehicle, and we're not quite at that level of confidence yet to spend that level of money. For that level of test money, we can do a lot more in stationary systems and bring a lot more benefit to different applications. So
yes, indeed, I think that's one of the challenges as well. I feel like we got a ID, I think ID3 here. It's like in the winter time, you can easily only get like half of the mileage claimed. Absolutely.
It's typically 40 to 50% range impact, and so it's not all just the AC. Some of it is the power required to keep the battery at 20 Celsius. But even you said 2/3 of it is the passenger comfort, and 1/3 is keeping the battery comfort, if you like. If you can take 20% off that bill, that's a big help.
Okay. Yes, indeed. So that's my another probably follow-up question. And also you mentioned kind of control strategy. What are kind of main changes? I assume is dropping. So the principle of kind of control or moderate kind of capacity or thermal management should be very the same or similar.
Yeah.
Does it require a lot of control redevelopment or just fine tuning?
Really, just what we found with the high pressure blend, it's really just getting the gas cooler pressure control strategy right. And then with that Volkswagen system, getting the way you use I think there are only like 3 different refrigerant expansion valves, and how you balance the load across the valves turned out to be quite important for the blend. Whereas CO2 system was already well optimized and they got it as good as they possibly could. So we couldn't make it any better. But with the blend, we found a combination of gas cooler optimization and control strategy optimization was best. Charge determination was pretty easy. Use the same charge. But the other factors were really about the control. And that's been a constant for that blend. It's all about getting the pressure levels right. The second order optimization, we're working on if it was a scroll compressor, working in the profile of the scroll to optimize the volume change for the refrigerant. But that's the sort of thing you work with an OEM when you know there's a significant benefit and a significant market to do the work.
Yeah, sounds quite a strategy. Probably we're going to face the same thing as well during the replacement. I got a final one. Actually, I got a load, but I got a final one. Do you have any kind of property data available can share with like interesting like developers?
Yes, we do. Yes, if you contact ERA, then we have tables of data. We have pressure enthalpy diagrams. We have ref prop fluid models and so on. And we have summaries of refrigerant compatibility testing as well.
Oh, that's perfect. Thank you very much. Thank you.
Okay.
Thanks, Tuan. ERA.
Are we okay with the time, Amir?
Yeah, we should be okay. We'll make this the final question.
Okay, right. Thank you, Bob, for compiling all of this work into an hour. I know it's a lot of hard work and years of data compilation. This question is basically some comments and a question for my interest. So we all know that refrigerant is widely regulatory driven, and the regulatory regulations, they get restricted year by year, every year by year, and everyone wants like something like a magic refrigerant which has got every properties. It's like an ideal refrigerant which doesn't exist. How does Orbia position itself in this in day and age of competition with our competitors, with our products?
Yeah, I think, well, we basically try to be honest with people. And a good example is in the supermarket refrigeration sector. People want A1 refrigerants for their traditional supermarket designs because the refrigerant goes out to the store, and there's a potential for loss of refrigerant into the store, and so it needs to be and the store is not designed for flammable, so it needs to be non-flammable. That's fine, yeah. But then they want GWP less than 750. Okay, non-flammable fluids can be designed for 750, and then they want no temperature glide, and then they want the same performance as 404A. And at that point, we have to be the gentle but frank conversation that you can't have everything. And especially for a refrigerant where you're maybe running it as cold as -35, -40C in the evaporator, you need to sacrifice, basically, if you say non-flammability is a given, you have to sacrifice, and GWP has to be low, then you're basically sacrificing capacity, or you're dealing with quite a radically different temperature glide. And that's the point where it gets difficult. For air conditioning applications, where 134A would typically be used, it's easier. There are more fluid options. And indeed, the evolution of things like 444A shows you can get a pretty good refrigerant with very modest temperature glide and works very well, doesn't need much technical change. But when you go to other conditions, then you just have to be upfront with people and explain what goes on. The other differentiating factors are we strongly believe that we should focus on refrigerants that don't leave long-lasting breakdown products, and that's basically the backbone of what we're developing today.
Yes.
Niche refrigerants like 407A, where they're going to biomedical, we're using a small amount of 125 and a small amount of 23 for flammability management, because again, that application requires non-flammability. at least in today's technology. But it's as small as we can get it. And if people can start adapting to use weakly flammable blends instead of non-flammable blends, then we can actually remove the, if you like, the PFAS precursor content from those blends and go to simpler solutions.
Yeah.
That's really our philosophy, is to be honest with people, explain what's possible, and then work with them to try to come up with a solution that is as long-lasting as it can be.
Yeah. Thank you.
Brilliant. Thank you very much, Bob, for the presentation, and everyone for the questions. Very insightful, and a lot of innovations happening, and we had a good turnout as well. Just to reiterate that the session has been recorded, so if you've got anything that you want to refer to, we normally have an ASHRAE UK YouTube page, and I'll upload it there. It saves you the effort of flicking through the PowerPoint slides, and also it saves Bob the effort of explaining it once more as well. Thank you. Thank you, Bob.
Thank you very much, everybody.
Thank you very much. Bye for now.